Think about the math classes we grew up in. The job as teachers was to be a broadcaster. Teachers would open the book, show 3 examples, and give kids 25 problems to mimic. It wasn't easy, teaching's never been easy, but the path was a straight line. In an inquiry-based classroom, like what we're hearing about in building thinking classrooms or other problem-based methods, you've traded that straight line for a web. You give students a problem to solve, you stop, you let them think. That's brave teaching. But here's the thing, for this to work, to really help students learn, you have to do more than just let them solve the problem. You have to craftily connect various student strategies you see around the room. Many teachers think that the point of the inquiry-based teaching methods are to allow all students to just solve each problem in their own way, because everyone learns and thinks differently. However, that's actually not the point. We do ultimately want to use this open thinking to guide students so they can discover the specific strategies they might not have used on their own first. We do actually want to get students to ultimately learn how to solve problems with equations, with algorithms, and with standard procedures. But we want to do that all by embracing how students naturally approach the problems. Then we can use their own thinking to connect to other strategies. I'm going to show you 2 specific examples of how we can build this thinking in just a minute. How we can set students up to solve something on their own with their own thinking, then how we can connect that to a different strategy they might not have thought about on their own. Some teachers like to say that we're trying to get students to learn more efficient strategies. However, I want to push back on that a little bit, because an efficient strategy to one student might not actually be an efficient strategy to another student. And even deeper, an efficient strategy in one situation might not be the most efficient strategy in another situation. Instead of trying to teach students to become more efficient, I like to lean into, we want students to become more flexible, to understand there are different times when I might want to use different strategies, and different strategies might work better for different situations for different students. Now, here's the kicker. To do all this connecting of different strategies, teachers actually need a deeper understanding of the math than we ever needed in the old days. Not because the math is harder, but because we have to see the destination in a dozen different student paths all at once. And to be honest, in many different situations, we're expecting teachers to have almost a doctorate level of understanding of how students' brains learn math. And that's the challenge. Whether you're a new teacher or a 25-year veteran, there are very few teaching and professional development programs out there that really lean into this work. It's not any teacher's fault for not knowing this, it's just that the research in math learning takes a long time to filter down to the classrooms. That said, I've seen some amazing teachers lifting students up in tremendous ways with some of the connecting strategies I'm about to show you. So let's get to one example. Let's look at a real-world example. Say you're teaching multi-digit multiplication, like 12 times 15. There are 12 eggs in each dozen, and we have 15 dozen eggs. How many eggs do we have in all? You know, really important math questions kids are going to need when they get into the real world. In the old way, you just show them how to write the numbers into this algorithm, where to carry the 1, where to put the magic 0, all that great stuff. And that strategy still works. We're not saying to not help students learn this. However, jumping right to the algorithms often causes intense confusion for students. If you weren't one of those students who got confused by this, count yourself lucky, because there's some research that shows just jumping to the algorithm typically only works for about 25% of the students, meaning 75% of the students may have learned the skill for the short term, for the quiz, for the test, but by the end of the year they've forgotten it. They need to be retaught it every year over and over again. That's why we need to continue reteaching things. Okay, back to 12 times 15. In your thinking classroom, when you first give students a chance to find the answer on their own, a student might draw an area model like this, breaking the numbers into 10s and 1s. You see them doing it, and you're happy. They're engaged, but you're worried they won't actually get the algorithm, which is one of the standards we're supposed to get them to. So what can we do to help the students make those connections, instead of just getting an answer and moving on? Don't just say, great, see, we can all solve things in different ways. Isn't that wonderful? We're all different human beings. Instead, look for a student that found that 12 times 10 is 120, and ask, where do you see the 12 times 10 in this other model? Where do you see 12 times 10 in this model? And give them a minute to think about it. Give them a minute to process. This is a great time for a turn and talk to let every student have a chance to process. It can also be super helpful to write down that question that you're going to ask, both helpful for you, the teacher, and for the students to be able to refer to. Wait, what was the question the teacher just asked? The question is, where do you see the 120 in the other models we're looking at? Let's see how your different ideas connect to each other. The goal here is to help students realize that we can use different ways to represent thinking. As time progresses, students will begin to move back and forth between these different strategies. At the end of the lesson, you can ask, now that you've seen different strategies, which one do you like the most to solve problems like this? Or how is your original solution strategy the same as this other one? You're helping them to translate their own brain's logic into formal math. You're building the bridge, and this will create longer lasting connections in your students. That said, it does require you to have a stronger understanding of those connections yourself. Okay, middle school teachers, you might feel this too. Maybe you're working on ratios, like a faucet is leaking 3 cups every 2 minutes. How much will it leak in 10 minutes? You might have a student that solves a problem with a table like this. And you might think, that's a great, beautiful table, and that's wonderful. We can see it's gonna leak 15 cups in 10 minutes. And that's great additive thinking. However, you're responsible for getting them to linear equations and slope, not just finding the answer to one question. Instead of jumping to y equals 1.5x, though, we might think about, how can I help to transition from one student to the next? I might think about showing this student here and this student here and saying, hey, what I'm noticing is I can begin to see there's a pattern, there's something happening with these. Where if I go from the number of minutes to the number of cups, what do we notice we're seeing? What's the pattern we're seeing? And maybe I even go a step further and say, let's go ahead and graph that in an x and y axis and see what do we notice and what does that slope mean when I refer back to the original table that we had. Your table shows that for every 2 minutes we add 3 cups. If we put this on a graph, how does that 3 cups per 2 minutes tell us how steep the line's going to be? By asking that question, you've just connected a table and a graph and the concept of slope in one breath. But you can only ask that question if you actually see the connection instantly. That's the doctorate level understanding I'm talking about. It's the ability to see the math inside the student thinking. If this feels like it's a lot, that's because it is. We're asking you to make split-second pedagogical decisions that require a massive amount of mental energy. So how do teachers handle this all? The best way I've seen this work is to preview that math problem before class even starts. And before you teach it, sit down yourself and write out 5 messy different ways a student might try to solve it. Then try to find what's your purposeful connecting question you might ask to connect those different strategies. Or maybe the multiple strategies. And write that question down. Write it down on paper. Write it down on a slide so you don't forget to ask it. Because that question is so vitally important. You don't have to be perfect. You just have to keep building those bridges. You're doing the hard work of making sure kids don't just do the math, but that they actually understand it, understand what it means. The biggest takeaway here is to move away from, great, we all have an answer and we all solve things in different ways because we're all different, isn't that wonderful? And move to, how do some of the different strategies we've seen connect to each other? That's where you actually build mathematical understanding, mathematical thinking. In the comments, share a math concept that you've seen is difficult for students to understand. I'll put together some more videos showing how we can connect prior knowledge of students so that they do have a better understanding and they can build off their knowledge to learn new content.